All right, today we're going to be learning about scatterplots and association. Scatterplots are something that you've seen and you'll probably recognize from grades prior. Today we're going to talk about how it relates to linear relationships. So scatterplots are graphs that use points to display relationships between two sets of numerical data and can be useful for observing trends, patterns, or association between two variables. So association is just like a relationship, okay? If the overall shape of the data resembles a line, then that association is described as linear. So here we have three examples of scatter plots, and they have three different types of relationships. So the first one shows a positive scatter plot, and that's because as the x value increases, the y value also increases. So if they're both increasing, it's positive. The second one shows a negative relationship. So as the x value increases, the y value decreases. So you have one increasing and one decreasing. And then there's also this hot mess, which we would call no association, because it's not increasing nor is it decreasing. The change in one variable has no effect on the other. Now, association and causation are two different things. Causation exists between two variables when one changes affects the other. So think cause and effect is causation. So when we look above, it says describe which scatter plots above show causation. We read our variable and we say, does this person's age directly affect the pairs of socks they own? No, obviously not, right? Your age does not directly affect the number of socks you own. Do snow cone sales directly affect sweater sales? Well, when we think about the words direct effect, we know they have a relationship. It's shown in the scatter plot, but when we think of direct effect, truly it's the temperature that's affecting snow cone sales and sweater sales, right? Sweater sales goes up because the temperature goes down. Snow cone sales go down because the temperature goes down. So they do not have a direct effect on each other, therefore it's not causation. Now here in our positive, our hours studied directly affects the exam score. So we would say hours studied directly affects, and I want you to write exactly those words, exam score, therefore shows causation. Hours studied directly affects exam score, therefore shows causation. All right, for each pair of the variables in the table below, describe the association and whether you'd expect there to be causation between the variables. So first we decide association. Is it positive or negative? As the number of cars in a restaurant parking lot increases, the number of available seats decreases. Because one is increasing and the other is decreasing, this would be a negative association. Does it show causation? I would say yes, because it specifically says the restaurant parking lot. So the number of spaces available directly affects the number of people at the restaurant. Right? Now, I understand there's some variables here, and that's why it's a scatter plot, right? So I understand some people ride together to a restaurant, some people ride separately, but that is why it would be considered a scatter plot and not a simple linear function. All right? As your height each year since birth increases, the average annual price of gas increases. Because both are increasing, I would say this is a positive association. But when I think about causation, does my height have a direct effect on gas prices? No, because height does not have a direct effect on gas prices. Here, I'm trying to make it all fit and it just ends up looking goofy. There we go. So now the one thing that would actually be directly affecting our height would be time passing, right? So average price of gas is increasing, time passes, increases your height. So the time passing would have a direct effect, but the height does not directly affect gas prices. Now, both scatter plots on the right display what type of association? Well, when we look at these and look at the trend or the direction that it's going up from left to right. So we would call this a positive association. When we go to predict which one is stronger, I'm looking at the points, and I'm going to go ahead and predict that B is stronger because the points are closer together. All right. Now, association can also be referred to as correlation. Correlation and association are synonyms. The more the points are spread or scattered, the weaker the linear correlation. The closer the points are to one another, or more like a shape of a line, the stronger the linear correlation, right? Because it looks more like a line. So our prediction was correct. Correlation coefficient can be represented by the letter R, and it's a value anywhere from -1 to 1, which seems silly that it's only in such a small space. But if you think about it, 0 would be your no correlation. And then if you have a really strong correlation, but it's negative, that's close to -1. So the negative numbers closer to 0 would be weak. Okay? So then a number closer to 1 would be a strong positive, and the positive numbers closer to 0 would be weak positive. So that means they're scattered. So if I were to look at this with an actual table, and you can include these tables here, I'm just going to do a little example here, and then we'll look at some more examples. My no correlation is just a mess, right? It's not going up, it's not going down, they're just scattered everywhere. So that means that my weak negative is pretty scattered, but there's somewhat of a trend going down. And my weak positive is really scattered, but somewhat of a trend going up. Okay? Now that would mean my strong positive goes up, but very close to a line, and my strong negative is going down, but very close to a line. So as you can see, it goes from like a negative line to negative scatter to very scattered, no direction, to scattered going upward to a scattered upward line. Okay, so we just transition through from -1 to 1. Now, here are 4 examples, and we're not actually doing the calculation, we're just doing comparison. We're trying to assign the R values based on what we know about weak positive, weak negative, strong negative, to the numbers on the right, or excuse me, on the left. So both A and C are negative, so they must be one of these two. Now, I would say C looks stronger than A, so it has to be closer to -1. So I would say the R value here is -0.9. Therefore, the R value for A is -0.5. For B and D, they're both positive. Okay, B is definitely stronger than D, but I'm going to have to use my positive R values. So B, I need closer to 1, so I'd say 0.8, and D, I need closer to 0, so I'd say 0.2. So understanding greater than less than of decimals here is very important. Now we can also calculate R values, and to do this we're going to have to use Desmos. So I'm going to dual screen here, so I know it's going to get a little bit small, and that's okay. But you can also get these directions from your teacher or on the daily slides. So I'm going to select plus and add a new table. Now, when I'm looking at my example, it talks about the times they practiced their line versus how many mistakes they made. Generally, when you're looking at a table, the top variable is your X, the bottom variable is your Y. If you have a horizontal table, the top is X and the bottom's Y. So in my table, I have X1, Y1. If I were to add another table, I would have X2, Y2, but I'm only going to do one at a time. I'm going to enter all my X values. And I need to do so carefully, so I'm just going to double check. 10, 2, 8, 6, 1, 3, 11, 7. Yes. Now I'm going to go back to the top and enter all my Y values. And when I do, I'm making sure I'm looking back and forth to make sure my correct numbers are lining up. So like when my x is 6, my y is 2. It shows the same here on my graph. When my x is 1, my y is 6. And this is a scatter plot, so you can see that as I'm typing these, it's creating a scatter plot on my graph. Now, just a little trick about Desmos. You can click and drag it around. You can zoom in and out to see all the points. And if you're ever lost or you get really out of the regular view, you can click this little home that says default viewport, and it'll just go back to the original. So I'm going to drag over here. And then to find our correlation coefficient, we are going to click on this add regression. And we want to make sure we're on linear regression because it's creating a line. Now you'll notice we've not exactly connected these. I can look at my x and y intercept. I don't need them right now, but I can see them. But this is showing me approximately the trend of the points. Okay, so this is the equation for the trend line. The correlation coefficient is the R value. So you're not looking at the R squared, you're looking at the R. And it says, find the correlation coefficient to the nearest hundredth. So that's your R equals. Well, our R equals negative 0.9342. My 3 showed up funny. I'm going to go back big to this page, so it will let me write a 3. And then it says round to the nearest hundredth. Well, when we're rounding to the nearest hundredth, here's our little wrap to remember this. Find your place, look next door, 5 or greater, add 1 more. So because there's a 4 to the right of the 3, I'm not going to add 1 more because it's not 5 or greater. All digits in front stay the same. So we have 0.9 and 3 stays the same. All digits behind, 0 is your name. So everything else becomes 0 and I don't need to write them. So my correlation coefficient to the nearest hundredth is negative 0.93. If we go back to our line, we'll notice just by observing it's a negative and the points are pretty close to the line. So without even knowing our number, we could predict that it is a strong negative association. Strong negative association. Okay, let's go on to the next one. Principal Thomas recorded the number of students at his school who were members of both the robotics club and the photography club every year since they each began in 2012. Find R to the nearest hundredth. So again, we're looking for the correlation coefficient. I'm going to go back to Desmos and X this out so it clears it and start with a fresh table. Now, my robotics is going to be my X values because again, your numerator, or excuse me, not your numerator, your top row is normally your X, your bottom row is normally your Y. And I'm going to plug in my X values into my table. 6, 9, 12, 20, 22, 37, 31, and 26. And then my Y values, 21, 18, 38, 50, 46, 61, 60, 78. Okay, I'm going to press my add regression, and I actually couldn't see my points before, even in default viewport, so I need to scroll out to see them. Now this time I see that it's a positive association. And it does look strong. When I go down to my R value again, that confirms that it's a strong positive because it's 0.8472. So that's what I'm going to write here, and then I'm going to round it. 0.8472. Now, when I round, find my place, look next door, 5 or greater, add 1 more. So I added 1 more because 7 is greater than 5. All digits in front stay the same. I add 1 more. All digits behind, 0 is your name. Okay, so my R value is 0.85. And like we predicted, this is a strong positive association. Now, do either of these tables represent causation? Remember, causation is direct effect. Think cause and effect. Do the number of kids on the robotics team directly affect the number of kids in the photography club? No, because obviously they can be in both, they could be in one or the other, they could be in none. But do the number of times somebody practices their lines directly affect the number of mistakes they make? Yes. So, number of times practicing lines directly, I'm going to capitalize, affects number of mistakes made, therefore showing causation. You don't have to do it in all caps, but circle it, underline something. Directly affect is so important to understand when thinking causation, because you can think cause and effect. All right, that's all for the 4.1 notes. If you have any questions, ask your teacher. You can also go back and rewatch. Thanks for coming, and we'll see you guys soon.